is based on his interest, based on the research area of himself and his boss in his primary group, plus some knowledge transfer skills that we practiced at the beginning of the summer. So it will be non-adiabatic dynamics of photoexcitation leading to charge transfer, at least ideally. And if we see some options to suggest either improvement of the results, ways they obtain, or interpretation, I believe Amir will be not against it. So floor is yours. We all are very curious to hear.
Thank you very much, Dr. Kilin. This project is a follow-up from our first project with Dr. Kilin group. So in the first project, we investigated the ground state electronic structure of the PDPP conjugated polymers, and we started to work more on this project with actually addition some additives and make it as a blend of PCBM and ITIC, which are two most well-known options to make a blend with the conjugated polymers to tune their both mechanical and electronic structures. So as you know, conjugated polymers are attracting a lot of attention for the solar cells because of the easier manufacturing process and also cheaper manufacturing process again. But to date, if they want to compete against the traditional semiconductors, silicon, the power efficiency is not still good enough to bring them into the first rank of the usage in the industry. So because of this, a lot of research area is focused in the development of the conjugated polymers, some photovoltaic performance and their power conversion efficiency. For instance, for the silicon, we have right now power conversion efficiency, PCE of 20%, but for the most conjugated polymer is around or less than 10%. So because of this, there are a lot of rooms to research on this area. There are two options for make the blend with conjugated polymers. One of them a traditional option, and maybe one of the best and available option is PCBM. Usually the PCBM provide a good electromobility, and it's could be a good match to or practical choice for as an acceptor unit for the conjugated polymers. But there are pros and cons for this blend. How they improve the electronic properties of conjugated polymers, but at some sense they badly affect the absorption spectrum because they cause also some aggregation in the conjugated polymer systems. So for some polymers, those aggregation may cause some problems. So one of the items that we wanted to check maybe in another project, not directly here, is to investigate, for instance, the influence of the PCBM on the morphology of the conjugated polymers. Another brand new, almost brand new blend for the conjugated polymer is ITIC. It is introduced in 2016 for the first time. Usually this system is more compatible with the conjugated polymers, as you can see. Let me turn on the laser pointer. Yeah, the chemical structure is very similar to the conjugated polymer. Usually there is a backbone, a conjugated backbone, and also some alkyl side group grafted in both sides to control the mechanical properties of this kind of additives. So this could be an option. We do not talk that much about this ITIC today, but I was still running some simulation and calculation for that model. So Acceptor units usually we add acceptor units to improve the charge transfer between the donor, which is the, for instance, conjugated polymer here, and the acceptor units. So we usually expect to have a lower level of energy. So as you know, in the nature, usually electrons tend to, overexcitation tend to go to the lower energy level and get relaxed. So because of this addition, some acceptor units in the system improve usually charge transfer and improve finally the conductivity of the systems. So for this system, we still have our previous model that we published in our previous paper. It consists of a periodic dimer of the conjugated polymers. So you can see that from the different perspectives. And we add one PCBM molecule into the simulation box. Then we do the ground state calculation, we optimize the system, and then start molecular dynamics calculation. And finally, we did some non-adiabatic coupling calculation on this model. So first of all, if we want to have a quick look on the partial charge and the orbital structure of this system, we can see that, for instance, HOMO orbital is appeared, which is number of 469, appeared on the backbone of the conjugated polymers, highest occupied orbital. And on the other side, as expected, the LUMO, lowest unoccupied orbital, appeared on the acceptor unit on the PCBM. So at least it represents the function of the PCBM as an acceptor in the current conjugated polymer blend system. So first of all, we have density of states for three different systems, DPP alone, PCBM, and ITIC. We used for all models that we are presenting here, we use the PBE functional. So PCBM, DPP showed a band gap of 0.82. However, both PCBM and ITIC exhibited a band gap larger than the DPP. So 1.47 for the PCBM and 1.13 electron volt for the ITIC. However, when we make the blend, we can see that addition of the PCBM to DPP and also ITIC to DPP both decrease the band gap and ended in a low gap blend. So both systems show the band gap around 0.5 electron volt. And so for sure, we can see a shift in the level of the HOMO and LUMO orbitals for those blend systems. So these are results that we have from the ground state calculation. Also, that was interesting for me. If we plot the level of energy for each system, DPP, PCBM, ITIC, and both blend, DPP plus PCBM and DPP plus ITIC. We can see that, so both of them, those blend have a higher HOMO value and a lower LUMO value of the original system. So Dr. Kilin, if I'm not wrong, you mentioned that for the blend, the LUMO would be the minimum of the three value of the system. Am I wrong, or can we discuss that later?
So this expectation would be correct if the units are separated by enough space, if the interaction is negligible. But when the units are brought together and start interacting, it modifies orbitals associated with both donor and acceptor. So if you see deviation from this expectation, it could be explained. Let's keep going.
Yeah, just one more comment. For instance, for me, I expected when I have two candidates as an acceptor unit, I expected to have a smaller level for the LUMO orbital. So when I put both of them near each other, electrons wanted to go from, for instance, the highest LUMO in the DPP, go to the lower LUMO in the acceptor unit. It happens for the ITIC. I saw that actually it fulfilled my expectation. The level of LUMO for ITIC was smaller than DPP, but for PCBM, I didn't see such that trend. So maybe this is not correct, my expectation. Am I right? Or
so what I see for your ITIC, it looks like LUMO is so low, then by bringing it to a contact to another molecule, it can borrow the electron from the neighbor unit in the ground state. So it could be not just changing, mutual change of the energies of orbitals, but also repopulation. So it is, to analyze it, maybe one needs to show not only HOMO and LUMO, but few other orbitals like HOMO -1, LUMO +1. And
okay.
This repopulation of orbitals in respect to independent units is the case for p-n doped silicon, when in the ground state there is already charge transfer at the interface.
Okay. Okay. Thank you. So yeah, the another things that we are just briefly comparing these two systems, and then we mostly focus on the DPP PCBM dynamic calculation. So one of the major difference also for both systems between ITIC and the PCBM as blend is poor absorption spectrum of the PCBM. However, usually ITIC exhibited a stronger absorption for these materials. We tested the absorption spectrum for these two standalone molecules, PCBM and ITIC, and as was shown before, ITIC exhibited a higher absorption spectrum. However, when we tested the absorption for three systems, pure DPP, DPP plus PCBM, and DPP plus ITIC, I didn't see any improvement, at least in the peak of the absorption spectrum. For instance, I expected a redshifted results maybe for both blend system, but first all systems show a peak at the same level almost, and both DPP and ITIC also show a similar trend for this system. So one thing that one can say, maybe this is just a 1D periodic model. So maybe in the real experiment, people see such that big difference for the ITIC because they are investigating a sample, for instance, in the unit of maybe several nanometers. So maybe some aggregation or some morphological properties cause such a difference. But at the first principle calculation, maybe we could not observe such a trends in the results. So
Can you discuss briefly right now?
Sure.
So, question to Amir, why do you expect an improvement in the absorption?
So
Is it the goal?
Is it the goal or no? So one of the logics that people come up with the ITIC as an alternative for PCBM is the higher absorption spectrum. But this is a problem. It's just because of the electronic structure or no? It's because of some macroscopy properties of the ITIC and DPP. For instance, the system has the same behavior at a one-dimensional periodic model as a bulk model in the real experiment. So this is one thing that people are interested to know. So, and also from the absorption spectrum that we showed in the previous slide, we saw that the ITIC showed a higher absorption. However, as a blend, we didn't see any big difference.
Okay. I will say a few words and then ask Aaron to help. If one would redo these three spectra with better functional HSC, everything will be blue shifted, right? It will be shifted from near infrared to the visible.
Mm-hmm.
But the sequence of the peaks is expected to be approximately the same. Now, on this figure, between 800 and 1300, there is a green peak available for ITIC, which is not available in other, right?
Mm-hmm.
So hopefully with HSC calculation, it will be a strong peak in the visible range. So now I would like to ask help of Aaron in sharing what one would expect as a philosophy of such calculations and such setup of blends, maybe related to your very first paper on perovskite nanowires and whole acceptor. Like, just would you please share in freestyle the idea of photo-induced charge transfer?
I guess like the crudest approximation would be assuming that there's not a lot of interaction between the two, like donor and acceptor, that you'd expect the absorption spectra for the joint system to be like spectra of like DPP plus spectra of PCBM. So those would be like the most dominant peaks. And then you might get some additional from like a charge transfers or like the interactions between the two. But those are usually like less intense. So my guess would be is that your spectra would be dominated by the DPP, since that one seems to have a higher absorption than the PCBM.
Okay.
So do you think if we, okay, go ahead.
Please.
As Dr. Killen suggested, if we use a different functional, or also if we use some, for instance, sampling techniques, we will observe same trend, or the conclusion may be different.
I mean, with functional, the biggest change will be like blue shift or red shift in the peaks. And yeah, if there are charge transfer contributions, those will change with functional as well. But I guess, yeah, I don't know if the overall picture would change very much with change in functional. But it's something to always check, though, just in case a reviewer asks.
Okay.
Let me express a thought in a rough way, and then maybe take help of Aaron to refine it. So the absorption by its nature typically happens without charge transfer. So it is promotion of electron from occupied to unoccupied orbital in the same spatial location. So it will be either in DPP or in ITIC. And it will be the peak in absorption corresponding to either one of the units. Then, during the thermally induced dynamics, the carriers will find their way to end up on different units. And so to transfer electron hole in different locations in space. And this charge transfer is the main goal for photovoltaics, to create a charge transfer state, which is much harder to create by direct photoabsorption. So it needs to be absorption plus some additional charge transfer events. Amir, does it make sense? Aaron, would you like to refine the statement maybe in a shorter way and in relation to this figure?
I don't know. I guess if Amir wanted to prove it to himself conclusively, just compute the spectra of DPP and PCM by themselves, and then just add them together and see if you get the DPP plus PCM spectra. If you do, that kind of implies that there's not a lot of charge transfer absorptions.
The lowest transition in the system that exhibits charge transfer is expected to be either completely dark or at least darker than in the original independent systems. So if upon bringing donor and acceptor together, the lowest transition becomes darker, it would be quite expected. Whew. Okay, yeah, sorry for the long discussion. Please go ahead.
Thank you for your comments. Okay, so the next step is to starting the non-adiabatic coupling, mostly of we will see some results for pure DPP and also DPP plus PCBM model. So the title is wrong here. So this is the system consists of the periodic dimer of DPP and PCBM molecule in the simulation box. So this is the simulation at 300K for the temperature. So first we did the calculation to calculate the Redfield tensor and also check the autocorrelation function. We expected to see the autocorrelation function to fluctuate maybe near the zero value. So if it converges very soon, maybe in 300, 400, or 500 femtosecond, we can expect that maybe coupling calculation for that time step or time span is also good enough. So the right figure is actually a Redfield tensor. So X and Y axis show the electronic states, and Z axis here represent the rate of the transition. So as you can see, the main value are concentrated along the diagonal. So it means that when we get far away from the diagonal, almost the rest of the value are 0. So it means that, for instance, for this area, most transition happen between the valence and valence electronic states, and also valence band to valence band, and also conduction band to conduction band. So also for the transition near HOMO to LUMO, we can see that the values are negligible. So we will use this calculation in the next step to do the dynamic relaxation dynamic calculation. So as Dr. Killian suggested, to choose the initial state for choosing the initial transition candidate, I choose the top 5 largest actually electronic states that showed up higher or larger oscillator strength. So for instance, for this system, we start first for DPP pure polymer model, we started from 312 to 313, and also another 4 values that showed higher oscillator strength value. So these are 5 different states. So for us, HOMO and LUMO are, HOMO is 312 and LUMO 313. So there are 2 parameters in our MATLAB code that we needed to adjust to set up the initial candidates for the starting the relaxation dynamic calculations. So there are 5 different values here. For instance, IH 1 to 1, 4 to 1. So we start from these conditions and then do the dynamic calculations for the rest of the simulation. So for each transition state, we have a KE and KH value in our code that represent the relaxation for the electron and for holes. So the first orbitals that showed the highest oscillator strength was 312 to 313. Actually, it's going from HOMO to LUMO. As we can see that we saw that in Redfield tensor also, we didn't see any transition in between those 2. So we just have a horizontal line for both electrons and holes. And usually we have a non-value for those relaxations. So this is because electrons are already in their lowest energy states. So, sorry, in the following figures, we should know that dashed and solid lines indicate the expectation value for the energy, for the conduction band, and also for the valence band. So the next step is, the next initial condition is 309 to 313 electronic states. Still for the electron, we have horizontal lines, and for the hole, we have the value. So it means that the current value is maybe not a good candidate. So for the next one, it's going from 303 to 314. Here we can see that we started from HOMO minus 9 value in the valence band to LUMO plus 1. And after a while, we can see that the system is relaxed and get a plateau, for instance, to HOMO and LUMO here. So this is also still my question from everybody here that knows this calculation. At the end, which transition state we need to choose as the final or representative model for our polymer system. So that was the model number 3. Yeah, for previous model, I didn't show the electronic dynamics, actually the distribution of the electrons through the Z direction. Z direction is showed here at the same scale and same dimension. You can see electronic dynamics distribution. So as it is expected for the pure polymer system, all of them are distributed along the backbone direction. Same situation also for the distribution of the hole in the dynamic hole dynamics in the Z direction, and for both electron and holes where the electrons are red or orange or yellowish colors, and the holes are shown in the blue. So again, both of them in the background direction actually level. So the rest of calculation, I'm just showing and repeating these kind of figures. It could be a little boring, but we need to see how the results are changed for the pure DPP and also for DPP plus PCBM model.
So if things are getting along the same pattern, would you please interpret this rightmost figure? So what does this orange and blue represent, and why they both are staying near the z = 0? So that we have some pattern to analyze for the future slides.
Yes, thank you, Dr. Kilin. So first of all, for the conjugated polymers, we in our previous paper also we showed that the most contribution of the electronic structure is because of the conjugated backbones in the system, and we do not expect any electronic influence from the alkyl side group. So here, both holes and holes which are presented in the orange color, and the blue colors that represent the holes are directed in the z = 0 levels, which is the level of the backbone. So, but why they show up, for instance, a concentration at this time, and then start for maybe some dissipation, I'm not sure. So you may help me with this, why we have such that difference as time goes, or
if we explore different orbitals of slightly different symmetry, like pi orbitals, which are more protruding away from the plane of this polymer, but you've told the main observation that the charge density of both electrons and holes stay on the backbone. Yeah, thank you.
Thank you. Okay, and the system number 4, actually transition state, initial transition state number 4 is going from 310 to 315, which IH and IA value of equal 3. We can see that relaxation for electron is around 0.1, and for hole is around 1.5. And again, after time, actually, after a certain time, they get plateau to the HOMO and LUMO value. Again, for the distribution of the electrons, similar to the previous transition state, we have the distribution for electron and holes, and both electron and holes in the level of the backbone in the periodic model. And the last initial transition state is going from 296 to 317, showed again 2 different KE and KH value, and the trend was similar to the previous one. After a void, they get plateau after around 1 picosecond, get plateau to the level of HOMO and LUMO. Again, the electronic transition for distribution, also hole distribution, and electron and hole distribution is represented for the backbone direction, actually. So any questions so far for this pure polymer model? Okay, so the next system is DPP plus PCBM model. Again, Redfield tensor is represented, and also autocorrelation function. So Redfield for Redfield tensor, the results are presented for HOMO minus 29 to LUMO plus 29. Around 60 orbital are investigated. And similar to the pure DPP, we saw that the most transition happened between valence to valence band and conduction to conduction band. And as we get far from the main diagonal, we can see that the transition rate is near the zero. And again, autocorrelation is fluctuating a lot around the zero. But I have a question, Dr. Kilin or Aaron, do you have any comment on this? It seems that sometimes fluctuation is going near even 0.5, for instance, after 500 or 600 femtosecond. Is it healthy simulation or?
So the model is isolated, it is closed as one performs the simulations. So that when we compute couplings, the mechanism for energy dissipation is not activated. And therefore, same as in classical mechanics, if you have system with few degrees of freedom, there is a chance that after long enough dynamics, it will come into initial condition. So this could be a numerical effect of the same nature. So because the system is closed at the during the procedure of generating couplings, it may demonstrate constructive interference after a long time. But this is an artifact, and we shouldn't worry about it.
That's great. Thank you, Dr. Klein. And the same procedure for the PCBM blend, DPP plus PCBM, we chose the 5 orbitals with highest oscillator strengths to do the calculation. So,
Amir, I apologize for interrupting in the middle. I want to give you a maybe not killer question, but a challenging question. So, in the 6 transitions that you have selected, would it be possible to show where they are on your slide where you did show absorption spectrum of combined system? Like which peaks on the absorption spectrum correspond to these transitions? It was something like slide maybe 8. Would it
I get the question.
And pick the peak.
Guys, it's a very good question.
So yeah, go ahead.
So usually the first peak of the absorption spectrum or main peak, if we consider the transition energy, should show the highest probability, right? The first peak is should be correlated with the largest oscillator strength, or I'm wrong?
Here the data are ordered according to oscillator strengths, according to intensity, and on the spectrum they are ordered according to transition energies or wavelength. So in your first 6, the lowest one is 2.8, which is about 3, which would be about 400 nanometers. So can we go to slide 8 and see if there is a peak of the combined system at around 400 nanometers?
Sure. For PCBM, yeah, we have a peak around.
So maybe so green line. Oh no,
No, the red line is
Okay.
DPP plus
You know,
PCBM.
let's go to the next red peak. Around 400, there is something. See this double peak. So maybe
Yes.
one of these small sub peaks corresponds to transitions that you have identified in your as your candidates.
Okay, I got your point. So you want to say that if you want to find some initial candidates, it's better to find those related to each peak in the absorption spectrum.
Yes, yes. This procedure of selecting initial conditions should go in cooperation with analysis of absorption spectrum.
Okay, this is an alternative way, or no? Somebody needs to consider, for instance, those oscillator strengths and also all peaks, then choose the final system.
It's not possible for a human to run all possible initial conditions, but and if you miss a couple of them, it's okay, but it's better to just show the comprehensive logic. And if you appeal to the absorption spectrum, it will be quite clear to experimental community what you are doing. So then you can explain, we excite our system at the wavelengths of 400 nanometers and explore the consequences of this excitation onto electron hole dynamics.
Very good, makes sense. Yeah, I got your point. Sure, I will include those calculations also to my current results. Thank you. That was a good point. Okay. Okay. Any question? Okay, let's keep continuing. So, yeah, at least for this presentation here, we have the initial transition from the highest oscillator strengths, but I will add those transition from related to the peak of the absorption spectrum. So 5 different states that were chosen are shown here. Again, HUMO and LUMO are 469 to 470, but we can see that this time the HUMO and LUMO are not appeared between this transition from 5 largest oscillator strengths. So the first peak, the first transition, the result shows here. So for top line, the transition energy is from HUMO minus 8, and for the bottom line is LUMO plus 7. And as it's expected, after a certain time, a critical value of the system is relaxed and converged to the final energy level. And for this system, for this transition, for the blend, you can see that for the electrons here. First question here, Dr. Kinney, if we want to judge the system, the electronic structure, should we explain both electron holes separately or no, just at the same system, both electron hole distribution?
Please repeat the question, I didn't get it.
So in our code we had the distribution of electrons, and in the same separate figure distribution of holes and the distributions of the electron and holes are the same. So it's more illustrative if we show electron and holes.
Later on, especially for publications, it's more illustrative if you analyze both simultaneously, electron and hole. But for now, it's okay to look on electrons, and I wanted to ask you to make a little slow down here and interpret what we see on this rightmost panel.
Okay, so this is again the Z dimension of both figure has the same size and is located at the same level to have a better visual inspection. For this system, so the orange spots are showed up mostly around the acceptor units, and some points also along the backbone. And for the whole,
no, wait, we're not done. So this single figure is worth of maybe a standalone paper. One can tell long stories. So keep explaining what is going on. Like, what is scenario of a movie? What is happening here?
So the blue spots here represented the holes, and the orange represent the electrons. So here we have the most distribution for the near the in the level of acceptor units. So the other things that I can say, the over the time, this distribution is a little changed, but keep the same pattern at least. And
so blue is a background. Here there are no holes. It's just we are looking for electronic. So can you please tell how long the electrons stay in the originally excited LUMO +7 orbital? Or how many picoseconds or femtoseconds?
Maybe less than 1 picosecond here.
But can you read the X label? Oh, and you can show it by your
until here, maybe.
Yeah. Okay. So how many? How do we read the X-axis?
Maybe it's around 0.4 or 0.5 picosecond.
It should be less. So it is between 10 to -2 and 10 to -1. So it is between 0.1 and 0.01.
Oh, okay.
So it may be 50 femtoseconds, something like that. And what happens then? Where electrons go? Where does the electron go after 50 femtoseconds?
So we have some movement, appearing some electron in the backbone also. So this is kind of charge transfer at that time between two systems. Donor and acceptor.
How long this charge transfer state resides? What's the lifetime of this charge transfer state?
Maybe for another 400 femtosecond or less.
Okay, and what happens to the electron then?
Then again, we have another transfer to the acceptor unit.
So it's back transfer.
Yes, transfer back to acceptor unit for another maybe 100 or 200 femtosecond time span. And at the end, the system, I don't know, get relaxed, the electronic structure. So
well, first at about 10 femtoseconds, it jumps back to the backbone, right?
Yeah, for the few femtosecond.
And then returns to the final state on likely LUMO, which resides on the PCBM.
Yes.
So it's about 1, 2, 3, 4 charge transfer events illustrated in this figure.
Yes.
Okay.
Yeah, thank you for that. Same procedure for the holes. We have the results as a distribution is Z direction. So for the holes, we can see that the simulation, as simulation get started, we have holes in both level, the level of acceptor and also the level of the backbone. So
Amir, so in a second, please continue to analyze, but we should double check that the version of the code doesn't have a bug. This whole distribution looks suspicious because it is symmetric in respect to 0. while the model is not symmetric in respect to zero. Maybe there are some leftovers from previous versions of code where the charge distribution is symmetrized in respect to z equals 0, which is reasonable for a bulk, but definitely is not okay for such charge transfer system.
Okay.
Let's be cautious, and there is a chance that upon debugging, this figure will change drastically, and anywhere where this data enters will change as well.
Okay. Okay. I will double check. So, yeah, the next item is the electron hole distribution. So at the beginning of the simulation, we have electrons on the acceptor units and the holes, blue spots in the donor in the conjugated polymer. So at this certain time, we have a change in the level of the electron and the holes. But after simulation, or after time goes, we can see that for the rest of the simulation, until getting the relaxation, we can see that the holes are on the backbone direction and the electrons are on the acceptor units. Also, there are some spots between two systems, also maybe near the oxidized group on the PCBM. So do you have any comment on this, Dr. Killian?
Would you agree that the amount of orange and blue at initial time is less than amount of orange and blue at final time? So as time passes by, the orange becomes more orange and blue becomes more blue. So yes, maybe the overall degree of charge transfer increases over time.
Yes. Yeah, we can see the largest intensity in the contour of the distribution.
Okay. It would be interesting to initially excite the system into the such pair of states which you showed here at about 0.1 picosecond, where both electron and hole are localized on the backbone, and then as time passes by, they separate.
You mean show the visualization at each time?
No, just select maybe initial condition. Aaron, would you like to comment on this? I see it goes correlated to your comment that you typed right now.
I missed what your question was.
There were no questions. I was suggesting to look at the configuration at logarithm of time equals -1 and create initial condition corresponding to this configuration. Then initial condition will have no charge transfer character, which you mentioned in your comment.
Yeah. I guess PCM is supposed to be the acceptor unit, right?
Yes.
For the electron acceptor. So, yeah, like an easier, I don't know, story to sell would be starting with an excitation that's just on the PCM, and then eventually the electron transfers to the, initial condition is on DPP, and then the electron eventually transfers to the PCM. So you don't have the yellow regions bouncing back and forth.
Any additional comment, Dr. Khalil?
No, let's go forward.
Okay, thank you. So the next step is second one that we investigated, going from HOMO -22 to LUMO +22 based on the oscillator strengths. Here for the electron relaxation, we saw the same trend to the previous state, but for the hole, we had a lot of fluctuation. But after a certain time, they get plateau to the LUMO level. So this is the question that I have. Is it normal for some transition state to see such a big fluctuation in the relaxation calculation, technically?
It's not good. Let's ask for the wisdom of Aaron, Yvonne, and maybe David Grobner of their experience how to avoid this artifact.
Yeah, I would be happy to learn.
Aaron, have you seen such fluctuations in your runs, and what were you doing in such circumstances?
I guess I have. I don't know exactly why it happens, but usually when you choose like IH and IE very close to the end of like your energy pop range, it becomes unstable. So it's just you choose values closer to the band gap.
Yeah, exactly. This is the case also here.
So, Aaron, you're telling that there is no enough, so to say, basis states. There is no enough quantum orbitals to describe dynamics. So when it's, if one wants to excite so high, then the range of orbitals should be like 2 or 3 times wider than your excitation.
More or less, yeah.
Okay. Any comments on this aspect from David?
I've only seen this once in my work, and I just did exactly what Aaron said to do. Okay.
Yvonne, did you met this error in the past to fight with it?
Yeah, I guess there is some numerical instability for our calculations. So I guess if you want to get rid of this problem, so you should use less amount of coupling valves. So for example, in your first step, in the correlation MATLAB code, maybe you use 1,000. So try to reduce the number, maybe use 500 or 200. Then in the next step, for this figure, maybe you can get a good image.
Yeah. Thank you. I agree. It looks a little strange, but if one makes an average over shorter trajectory, then there is some healthy noise penetrating into Redfield tensor that helps to avoid these fluctuations.
Okay, got it.
Yeah, thank you for discussion. Let's keep going.
Yeah, for this calculation, I had, I think, 800 coupling points on the same time step. So I choose all of them for this calculation. Okay, so for this initial state, HOMO -22 to LUMO +22, we saw that at the beginning of the simulation, we have the concentration of the electrons on the acceptor unit. As time goes around less than 1 femtosecond, picosecond, we see some shift or transfer from electron from the acceptor unit to the backbone. And shift back again, and another transfer around 1 picosecond to the DPP polymer, and again come back. And at the end of simulation, we saw the less electron concentration from than the beginning of the simulation, and also most of them are concentrated near the acceptor unit for this state. Again, for the holes, as you mentioned, it seems for all of them they are symmetric. So maybe there is something wrong by the code. So I will double check that. And for the electronic holes, again, we saw such that fluctuation again in the contour clots. So as Yulan mentioned, and Aaron also, and David, maybe if we do some numerical treatment, the result looks more healthy and less fluctuation. But overall, we can see the concentration of the electrons near the acceptor unit, and for the whole near the polymer backbone. So, and at the end, maybe we have an increase in charge transfer after system gets relaxed, as Dr. Kilin mentioned previously. So the next system is HOMO -5 to LUMO +5. As Aaron mentioned, when we get closer to the HOMO and LUMO, we have less fluctuation here. And as you can see that the simulation started at HOMO -1 and reached to HOMO energy level. Same for the holes also. And here, again, the electron concentration for this electronic state initial condition is appeared at around the acceptor unit. At some time, we have some transfer to the polymer backbone, but it comes back at the end near the acceptor unit. So again, let's skip the whole distribution, and for electron and holes, we can see that, as Dr. Kilin mentioned, again, at the end of the simulation, we see the more intense values for the both holes and the electrons. Again, holes near the backbone and the electrons near the acceptor units. I have a question here, Dr. Kilin. For most cases, we saw that electrons are near the acceptor units. When we say that acceptor, we usually, this is maybe a general preconception in my mind, I expected to have holes near the acceptor unit than the electrons. So is there any specific reason that we have electron concentration near the PCBM here than the DPP?
There is a chance that HOMO of this hybrid system will have a hybridized nature. So it will be for HOMO orbitals, there will be part of the charge density on both polymer and PCBM. So it would need to look on the HOMO orbital with different ISO values and inspect the integrated one-dimensional HOMO orbital when it corresponds to the file like parch underscore and then whatever will be 400 something.
Okay, yeah, that could be interesting also. Sure, I will explore that as well. And the next orbitals, again, when we get far away from HOMO and LUMO, we saw some fluctuation again in the results. But at the end, both electron and holes get relaxed to the HOMO and LUMO energy level. And for this electronic structure, we can see that again, at the initial of the simulation, we have concentration of the electrons near the PCBM. At the middle of the simulation, we have some charge transfer to the polymer backbone. But at the end, again, similar to the previous states that we observed, the transition is near the concentration of the electrons is near the PCBM molecule. And same situation for the electron and holes distribution. However, this time, maybe for this orbital, we have less concentration for the holes and electrons. And I think this is the last step, going from HOMO -7 to LUMO +7. This is the first, the fifth value in oscillator strength. So again, the system is get relaxed to the HOMO and LUMO energy level at the end. And the pattern of the electron distribution is similar to the first initial state that we explored here, concentration on the acceptor, some transfer to the DPP, again, come back to the PCBM, a smaller shift to the DPP, and at the end, charge is distributed near the acceptor unit. And the same situation for the electron holes. We can see here some concentration initially on the acceptor units. Some blue spots here represent the holes. Again, the time near maybe 0.4 or less, we have some shift, some transfer electrons from the PCBM to the DPP. But as time goes, we can see that the holes are relaxed around the polymer backbone, and the most electronic concentration is appeared around the PCBM molecule. Yeah, that was the last slide. So,
okay, please join me in thanking Amir for doing this advanced calculations and presenting them. So we have several lines of written questions in the chat line, but maybe there are some questions, right? Important feedback or questions right away in the verbal form. So any questions are very welcome, or to say, floor is open for discussion. So I can just offer something, a starting point for discussion. So for experimental photovoltaic cells, where is the absorption of the DPP and PCBM? Just roughly, can you tell it by words? Like, is it infrared, ultraviolet, visible?
For DPP plus PCBM?
Mm-hmm. Well, for PCBM, for DPP, and for their blend.
So for the DPP is around 800 nanometer.
Not based on your calculations, for experiment.
Yeah, we show in our previous paper that DPP, we compare our results to the experimental value is 800 nanometer.
Okay.
For the DPP, for the PCBM, it has a poor absorption performance. I had the experimental data here. You can see that it's near the 300 based on the different sizes of the fullerene and of the buckyball, I think.
Mm-hmm.
For the blend, I didn't see any experimental study.
Okay. Yeah, good. And
here
is a question based on this consideration. which range is 300 nanometers? Is it like infrared, visible, or ultraviolet?
It's ultraviolet, I think.
Okay. Is there enough solar energy in the UV range, or it would be better, higher efficiency to excite in visible or infrared?
I think it would be more ideal to have an absorption range of the, I don't know, near infrared or something like that.
Okay, so photo exciting the transitions which are intrinsic for PCBM would be not optimal experimentally. Because on experiment, they are too high in the energy. But in all calculations that you, or most calculations that you have presented, the initial excitations were showing involvement of PCBM at initial time. So in some sense, there is a suspicion that most of the excitations were promoting electron and hole located on the PCBM, which is, there is nothing wrong. It is a possible process, but it could be not optimal for applications. While the excitation of DVP, which you've told is in 800, it's like red or near infrared, is quite efficient for solar applications. And so it could be reasonable from application viewpoint to find such initial excitation, which would promote electron from occupied to unoccupied orbitals, both localized on DPP. Does it make sense?
Not completely. If you explain it a little more, I would appreciate that.
Aaron, would you like to share your vision of this point?
I guess one thing Amir didn't show, or at least I didn't recognize it, is did he do absorption of PCBM just by itself?
You mean just absorption of the PCB molecule, a standalone molecule?
Yeah.
Yes, we.
It seems like compared to experiment, there's a lot of overlap between the two.
Yeah, this is the absorption for the PCBM, but the results as expected are far away from the experiment via PB functional.
Yeah, well, I guess like the second and third peaks seem kind of reasonable, but for some reason that it almost looks like well, based on expectations, it seems like an artifact, but it's hard to know what.
So even for DPP, we didn't get results near the experiment before. So as you know, this functional underestimate the band gap and electronic configuration of the semiconductors. So if we want to have better results, for sure, we should follow same trend that we did in our previous paper. Better functional with some numerical treatment.
So there are two ways, the correct one and easy one. The correct one would be to redo everything, or at least absorption spectrum with HSE or even more advanced method. And then it will be, everything will be more comparable to experiment. And the easiest one, which can be a quick fix on a short time scale, is just to borrow the expected trends from experiment and being armored by this experimental noise, just intentionally select the initial excitation localized on for both electron and hole orbitals, localized on DPP, on the polymer.
Mhm.
So by absolute values of transition energies, it will be not right, but qualitatively it will have it will show right picture. And it is something that one can do in like half an hour if you already have all couplings. It will not require additional initial calculations. From other point of view, one can just systematically explore qualitatively different excitations. Electron and hole on polymer, electron and hole on buckyball, electron and polymer, hole and buckyball, electron and buckyball, hole and polymer, and then see what are the qualitative consequences of these 4 types of possible excitations. Yvonne, do you have any comments or critical suggestions on this aspect of selecting the initial conditions?
Not really.
Okay. So then let's go over the typed questions. Amir, would you like to look through them and maybe verbalize and answer? And if they look silly, especially my questions, you can skip them.
No. So slide 3 and 4, what is the role of the functional group? Slide 3 and 4. Can one get photovoltaic effects if the functional group is modified? Very good question. So at this
let me answer and then you'll go quicker forward.
Sure.
Solubility. The photovoltaic properties will not change. It's just a functional group to process for synthetic processing.
Okay. And okay, that was a good answer. Thank you. So which units play the role of the donor? Slide 6. So donor should be the conjugated polymer, and the acceptor unit should be the PCBM. Normally,
according to your arrow in this figure, the photoexcitation happens on the donor, which would mean that we should select DPP excitation as a starting point.
All right, this is just a figure that I started. I saved when I started my studies on this area. So slide 8 and 9, PCBM is acceptor of electrons. 8 and 9. So when we have the LUMO orbital appeared on the PCBM, we expected to have it as an acceptor unit.
Good.
So slide 7, is it possible to define ratio of DPP on to PCBM? Slide 7. Yeah, it's a very good, you're talking about the weight ratio, Aaron?
Yeah, something along those lines to try to compare to experiment, because I assume that's one of the main quantities they can measure.
It's a very important and a very good question. So usually for the PCBM blend, people use 1-to-1 weight ratio, same amount of the polymer and actually PCBM in the system. So this is the thing that I'm always thinking about that. So here it's just a 1D model, but from the force field molecular dynamic calculation, we started making a bulk system of the conjugated polymer plus PCBM and ITIC. So not for this project, I think it could be another follow-up study that I'm interested to work on it, is to pack, for instance, several chains of the maybe 3 or 4 dimer of the conjugated polymer, maybe 3, and insert the same amount of the weight, equal weight PCBM or ITIC into the system. Then do some force field molecular dynamic calculation, have an initial equilibrated system, and then do some calculation. For those kind of the system, they would be much more expensive. We talked also to Dr. Killian about that a couple of months ago. But as soon as we get some progress in the current project, we will do that kind of calculation. If Dr. Killian also is still interested. So yeah, but to have some comparison with experimental data, usually the weight ratio should be 1:1.
So I think in this case, so you have like 2 monomers for your DPP.
Mm-hmm.
So that's like a 2:1 molar ratio. And then from that, you
Something
could try
close to that.
Yeah, then you could try to work out what that would be in terms of mass.
Yeah, usually if we add another PCBM, maybe get closer to the experimental data, but I think this paper could be mostly be focused on the qualitative trends than quantitative. So, Dr. Killian, any comment on this?
I agree with you. Adding a second bucket ball would bring one closer to 1:1 ratio, but then it will be more complicated to analyze orbitals.
Exactly. And takes a lot of time to do coupling calculations. So next question about Dr. Rasulov. Why was selected very well investigated PCFC system and not something else investigated? For example, some other C60 functionalized structure. Again, thank you, Dr. Rasulov, for the good question. So at the beginning, we started with the traditional system, PCBM. So this functionalized group is, I think, mostly used system in the polymer community. But to address your comment, the another system is even much far away better than the fullerene is ITIC for conjugated polymer. We choose ITIC to cover this drawback. I hope, because I finished the calculation, all coupling calculation almost also for ITIC system, I hope we can include those results into the system, but choosing from different C60 functionalized groups, I was not interested in that. If I wanted to move from the PCBM to a better system, ITIC is my choice. So, and my reason is just because of the results, the paper published on this blend recently, starting from 2016. But if you have any a specific suggestion based on the C60, please let us know. We would be grateful to consider that.
Thank you, Amir. Yeah, was for me always interesting to see the trends between the kind of similar systems. So right now you took really dramatically different systems, right? So it's difficult to compare them and see what actually contributes to better acceptor. If you would take like 2, 3 more or less similar, at least in the core system, like a fullerene C60 and different functional groups, so you would see some kind of difference between them, and then you would be able to estimate what actually contributes to better acceptor, or I mean the changes in this, let's say, the ligand attached to the fullerene structure, what contributes to better acceptor and what's less. So you would make some kind of interesting conclusions, I would say. That's why I was asking. So why you choose the PCBM, and is there any chance to investigate something similar, some other system which is similar to PCBM? Since I think the PCBM kind of very well investigated, there are like maybe hundreds of papers related to that. So maybe all these kind of situations already discussed many times in some other papers. I'm not sure kind of you more aware about that probably, because you did some kind of preliminary investigation before you started probably all this stuff, right? Okay, one more question I have while I'm involved. So you say you did some kind of force field calculations where you build the whole system, right?
Mm-hmm.
Have you, so you optimized that, let's say the whole bulky system, the whole box, it's optimized, or you just started it, you have no idea how they are arranging all these PCBM molecules next to the backbone polymer? You have any idea? It's systematically arranged, or it's like more or less chaotical, like, you know, like in the clamps around some particular parts of the polymer?
So first of all, that force field is not for this model. We didn't do force field calculation here, but briefly we did some optimization before doing the calculation here. But for instance, you are talking about if we rotate the PCBM and do the calculation again, we have the same structure at the end. This is your question? The position of the polymer and blend?
Yeah, the position between the PCBM, I mean, position of PCBM according to the polymeric backbone. Mm-hmm. It's always like the same way, like you're showing over here, or it's a little bit differs from PCBM to PCBM, I mean, next to that backbone.
I think if we start from another system, another system with a different initial configuration, we should see some deviation or some difference in the results. Because as we talked about that before, as soon as we do not have a condensed system near the bulk DFT model and do some force field calculation before, we shouldn't expect to have a maybe how to say a permanent or a reliable constant structure in the system. Yeah, if I, for instance, rotate PCBM molecule 180 degree and repeat the calculation, I'm not sure the current electronic configuration or current arrangement would be the same at the end. So, but again, so here we want to take a look at maybe to some qualitative trend in the results. So the next time, for sure, it's better to pack several polymer chains and same amount of the molecular weight for the PCBM in the system, do the force field calculation. And that could be the system that for every initial configuration, we should expect the near the same final optimal geometry for the system. But here, I'm not sure. So if we change the orientation of the PCBM, we may see some differences in the results, but at least I hope that the results, the trend would be the same.
Okay. Okay. Yeah.
But that's
what I also thought. You know, as soon as you change a little bit position, the whole electronic picture gonna change pretty dramatically, right? So, and all these discussion explanation kind of not going to be the correct anymore, right? Because there's so many different combinations may happen. That's why I was asking, is that pretty systematically arranging next to the backbone, or it's a little bit always differ from one situation to another?
I think even if we do the force field calculations, as soon as we have such a small system and just one molecule in the system, any initial configuration should affect the results. But at least I hope it will capture trend at the end. So
okay.
Dr. Kilin is a very good comment. Do you have any additional comments on that?
Amir, would you please bring up the slide with your molecular dynamics used for the coupling?
Sure.
Maybe run it in a loopwise. So all concerns and comments were correct. And I'm not going to say that they're wrong and this is perfect results. They need to be addressed as already discussed. But if it would be already a protection of a paper from the reviewer, then one could say the following words. And again, they are not a complete picture. It's only just a discussion point. During long enough molecular dynamics, mutual configurations of the polymer backbone and buckyball explore a range of orientations. And in average, the structure along molecular dynamics will be equivalent to a very large system or ensemble of many systems with different orientations. So it's only words to protect. In fact, as you see at this relatively short dynamics, the orientation doesn't change dramatically. But if one would do it like 100 times longer, it would scan all mutual orientations and include them into the results. So it's ergodic hypothesis that average over trajectory is equivalent to average over ensemble.
Right. Yeah. So yeah, you're right. But there, of course, that's not the right now what we see in that simulation. It's kind of not the probably not the main let's say not the most probable configuration right now, right, in the system, because it may let's say they move around, because I don't see any pretty strong interactions of that PCBM with the backbone. So it's definitely can move around to some particular, to some extent.
Forces are small enough, so it's one of the local minimum, but the main objective disadvantage of this model that it is very fluffy. It has a lot of vacuum between these units. And the first thing on the way to make it perfect is to compress the model towards realistic density.
Mm-hmm. Yeah.
Which is very desired, but quite expensive on the DFT level. It needs synergy between force field and DFT approaches. There are keywords in VASP for simulations under constant pressure. One can, this would help, but it will be not instantaneous. It's another chapter.
Yeah, yeah, that's another kind of part of the study. Okay, anyway, thank you. Thank you, that was interesting, at least. So I have some additional ideas which I can discuss later.
Thank you, Dr.
So, yeah, with both of you, yeah, we'll see.
Yeah, the scary point is that both Dr. Rasulov and Dr. Killian are in my thesis committee, so
Yeah. Thanks.
so but I hope I can show some maybe projects later on the condensed system as Dr. Dimitri suggested. I'm not sure when, but as soon as we get some free time for that project, I'm interested in doing that also. And okay, the last question from Dr. Killian. ITIC is also electron acceptor. Yes, as soon as that was published in the 2015 or 2016 paper in Advanced Material, I think that was offered as an acceptor unit. Also for ITIC, similar to the PCBM that Dr. Rasulov mentioned, there are different functionalized ITIC systems also to improve the electronic structure of that system as well. So that was the last question, I think. So if there is any question, I would happy to answer.
Let's keep scrolling through chat line typed questions.
Oh, there are more questions. Sorry, I didn't say. So Aaron, how have you done PDOS analysis to identify peaks in DOS? No, we didn't do any partial density of states yet. So should we do that for this project? Aaron, Dr. Killian?
It could be reasonable, and you can request help from Aaron and from Yvonne. But there is a barrier on this way, because both PCBM and polymer are primarily composed of carbon. Then simple PDOS projecting on the carbon atoms will not help. One needs to select good carbons and bad carbons, like name each carbon, or just follow analysis of orbitals for special distribution of orbitals for each orbital energy.
Okay, thank you. Kia, could you please explain?
Professor?
Mm-hmm.
I mean, that the autocorrelation factor and time step, that one, the blue line, there is a fluctuation, and red and blue. So blue line refers for the HOMO orbital, and the red one for LUMO. Is it correct?
Not to a same orbital, if I'm not wrong. It's related to a transition. Is it right? Aaron maybe has a better answer for that.
Yeah, so each line would be like HOMO, LUMO,
Yeah.
HOMO minus 1 LUMO. So each line represents a transition.
So
Or-
which line represent for which orbital? Like blue and red. There is, I think there is green as well. There is 3 lines. So which line refers for which one? Which orbital actually?
Kia, I need to double check them later and add a legend. I'm not 100% sure which one we include here. I will double check and let you know.
Okay.
Do you want to read your question verbally, Kia, or do you want me to read that?
I'll read it.
Could you please explain a little bit why band gap is started decreasing when you use DPP
And
PC?
also, I think that x-axis is not correct, right? x-axis of the figure,
Mhm.
autocorrelation factor. Yeah, it's not correct, I think.
What do you mean?
The code actually shared by professor there, if you using that one, then when you will plot this one, its x-axis will be the log scale, in the log scale.
Could be, but just correlation function versus time, so you can show linearly or in the log scale. I think.
It's just a way to improve visual presentation, but it's not like correct and incorrect. It's
okay.
more visible.
Mm-hmm.
So why, Kia, you asked why increasing the PCBM and ITIC
Yeah,
decrease
it's
the band gap. So
mm-hmm.
I think addition of any additives compatible with the conjugated polymers would improve the charge transfer, charge mobility, and finally decrease the band gap. So some similar, if I'm not wrong, similar to the doping phenomena. So when you add an additive into the system, we expect a lower band gap in the system. And,
yeah, but in your slide, I saw that your when you choose the that combination DPP with PCBM and another one DPP with ITIC. Yeah. So band gap almost same, like for one combination, the first combination DPP and PCBM 0.55, and there is only 0.01 difference for the another combination. So why you choose this one? And if anyone want to use this polymer combination, conjugated polymer, so which one will be better?
Yeah, it's a good question. So it is reported that the ITIC showed a better performance on the system. We discussed that in the beginning. Maybe some properties come from the bulk behavior of the system. For instance, it was shown that PCBM cause some aggregation in the, or affect the aggregation in the polymer system, but the ITIC didn't cause such that problems in the bulk system. But here, so far in the electronic structure, at least for those cheap ground state calculation, we saw that the band gap or electronic structure didn't show a big difference for those blends. So right now we cannot say that which system is better or which model should have a better performance here, at least in the case of the ground state calculation. But considering some dynamic calculation, we may have some calculation for that. But I think using just 1D system will not provide a lot of insight to reject a model or suggest a model.
Amir, may I contribute to the discussion?
Sure, please.
Thank you. The question of here would be very much related to your slide 15, where you show this. Yes. So for the red line, there is a hybrid of polymer plus bucketball, and for green line is polymer plus this butterfly ITIC. So everything here in this figure is red shifted, but if one would use right functionals or borrow absorption spectra from experiment, everything will be blue shifted. So the peak between 1,300 and 1,800 will be about 900 nanometers in the near IR. The red maximum around 700 nanometers would be in the UV range. and between them, if you consider only PCBM, there will be no absorption in the visible, while solar radiation is kind of continuous distribution, and it communicates us a lot of power, especially in the visible range. So having additional absorption peak in the visible range would improve performance of the solar cell. And here it corresponds to this green peak, which here is located around 1000, but if one would redo everything with HSE, it would be maybe around 500 in the visible range. So this presence of the visible light absorption would help to accumulate more solar light and convert it into charge transfer and then electricity.
Thank you.
Thank you, Dr. Kile. So slide 14, PV functional. Yes, Dr. Kile, we use PV here. Dr. Kile, how to interpret none rates from HOMO to LUMO excitation. So, when we
you already answered it while presenting. So
okay.
there is no transition to anywhere, so it's not correct to define the rate.
Thank you. So slide 21, where are the units for the KE and KH? I don't know right now. I need to check.
So
should be any comment?
Yeah, please ask if anyone wants to help you. Amir, you can ask everyone one by one until you get some answer.
Okay, any volunteer? It should be in the unit of the time. Should it be, Dr. Green?
Actually, I think I already, what's the question? I already answered that question, right? What's the unit of that one?
So it doesn't matter, Kia. If you can give us an answer, it's better.
So few lines later, I think, yes, Kia does provide an answer. Would you please verbalize it?
Okay, so the KH means the value that what's the K means?
Relaxation of the holes and electrons,
yes,
KE and KH.
Yes. So the unit of this two is 1
over picosecond, you mean?
Picosecond, 1 over picosecond, yeah.
Yeah, I think they should be in the unit of the time.
Inverse to the time, right?
Inverse.
Inverse unit of the time, yeah.
Like miles per hour, divided by time.
Yes. Okay, so okay, slide 23. It could be reasonable to combine energy distortion and space distribution in the same figure. 23. Yes, so I think you answered your question in the presentation. Actually, maybe it's more illustrative.
Yeah, it's just style of presenting it. It's not a question.
Thank you, Kia. Yeah, thank you. You ask and answer at the same time. Best type of question. So slides 40, initial condition looks like charge transfer excitation. Initial condition looks like charge transfer excitation. Can you explain more about your question, Aaron, please?
I guess I was just pointing out that, like, if you look at the initial condition,
Mhm.
like the yellow is on the PCM,
Mhm.
PCBM, and then the blue is on the DPP.
Mhm.
So it's electron and hole are separated, so it's like a charge transfer state.
Mhm.
And usually those are like lower in intensity. So is this one of your top 5 like oscillator strength transitions?
Mhm.
Oh, really?
I think that was the for the PCBM. That was, yeah, one of top 5. So I didn't get your question again.
It wasn't really a question. It was just more of a statement. Because I think at the time we
Okay.
were talking about it too.
Let me contribute. So
Mhm.
there are 2 aspects. One is fluency of Amir with speaking on this language of charge transfer. And second, possible bug in the code or in this version of the code that is fixed, can be fixed here or just upload another version. So part 1, language of charge transfer. Experimentally, it is expected that optically active states do not have charge transfer character. So both blue and orange are expected to be either on polymer or on buckyball. So if the initial conditions were chosen based on oscillator strengths, it is quite strange that immediately at the instant of charge transfer, at the instant of photoexcitation, there is a charge transfer. Things happen. It could be some interesting effect, but it is very unusual. And Aaron is referring to it. He's surprised that initial excitation has charge transfer character. So as I hear formulation of the question, I interpret Aaron's question as an expectation to see both blue and orange either in the range near 6 or both blue and orange at the range near -6 at initial time. Aaron, did I interpret it correctly?
Mm-hmm.
Okay, and the second part of this aspect, that if there is a bug and time-dependent distribution of holes as function of position includes the symmetrization, then in respect to 0 point, then it could be that this feature near -6 is not an actual observation, but it is an artifact because of symmetrization. It promotes whatever was at +6 to -6 and vice versa. So I would double check. So it is answer to Aaron. There is a chance that what we see on the figure that looks as initial charge transfer is a bug in the code that by quick fixing will disappear.
Okay, I will check the code if there is anything wrong.
A quick check would just be looking at the orbitals, just to see that they make sense compared to what you're seeing in MATLAB.
Mm-hmm. It's a great suggestion, and it will be quicker compared to debugging of the code.
What is the suggestion, Aaron?
Just download like HOMO -8 and LUMO +7 and look at them like in 3D, just to make sure that, or to see if the green figure agrees with what you see from looking at the 3D orbitals. So HOMO -8.
Okay.
If this is real, it's like you'd expect HOMO -8 to be on the DPP and then LUMA +7 to be on PCM. But if the orbitals differ, that probably indicates that the green figure, there's an error.
Okay. Okay, sure. Thank you.
Are there more questions to Amir or to anyone about the polymer to PCBM or ITIC acceptor? Questions 1, questions 2, question 3. So please join me in thanking Amir for presentation and for brave answers to the questions. So next Tuesday, there are plans for research update from Yvonne. Yvonne, do you confirm?
Yes.
Okay, yeah, so it will be some story about the chemical reactions on the surface of nanotubes as a way to create bright defects. And I don't know if we have any meeting in 2 weeks. Maybe I'll just make a quick summary and we'll plan for the fall semester, because some activities related to the fall semester are already scheduled for that week. Like orientations and such. And maybe for the fall, there will be slightly different Zoom link, but I'll share and invite everyone so you can decide if you want to join. So meeting is done. Thanks again for an enthusiastic discussion. Thanks to presenter and everyone who asked questions. And everyone is welcome to disconnect. If there are some open questions to discuss, please stay connected and we will chat.